Hello and welcome students. So let us start today's lecture. This is course number MA415 Algebra, and this is lecture number 36. Okay, so now recall what we are discussing in our last lecture. So we are discussing about field extension K over F or whatever, yeah. And you choose an element, alpha belongs to K. I say that alpha is algebraic over F if it satisfy a polynomial over F, right? And the least degree monic irreducible polynomial over F such that alpha is a root of this polynomial, right? Alpha is the root, is called the minimal polynomial, right? Minimal polynomial of alpha over F, right? And then we define this by the symbol M alpha F. Okay, so this is a minimal polynomial over F. Okay, and we define the degree of okay, so this degree of alpha as the degree of the minimal polynomial. Degree of this polynomial is called the degree of the algebraic element alpha, right? For example, you choose say Qi is element of the form A plus IB, where AB are rational number. Okay, and you see that the degree of I, so I mean, so I should say specifically F degree, probably that is better. You can say that Q degree here is so can you guess what is the Q degree? So what is the minimal polynomial of I over x? So this is x squared plus 1, right? So this is 2. So this is actually degree of the minimal polynomial, which is nothing but x squared plus 1. Okay, over Q. Okay, so if you change the field, obviously your minimal polynomial will change and may change, obviously, and then the degree may change also. Okay, so then what is the straightforward? You can straightforward say one theorem from here, whatever we discussed so far. You can say that, okay, so so let Q over be an extension field and field and alpha belongs to K is algebraic over f. Okay, if this is given, then what you can say, then you can say that then so this the smallest subfield of k generated by f and alpha is actually isomorphic to this over the minimal polynomial of. Okay, and this is obvious because obviously we proved that if alpha last day we proved that if alpha if so the proof is obvious. Proof follows as we know that if alpha is the roots of some polynomial px which is irreducible over f, then this is this, right? Now we know that in this case this px is nothing but my minimal polynomial which is irreducible over f. Okay, so this is this, and not only that, you can also say what is the degree of this f alpha. Degree means dimension of vector space over f, and this is nothing but the degree of alpha, or you can say degree of mf, whatever that minimal polynomial, all are same. Okay, clear? So so obviously you can generate this by the minimal polynomial, and then you will have these simple extensions of alpha of f with alpha, right? Okay, so now you can say more things. You can say another important theorem from this, and that theorem tells you that whenever you have an algebraic element, then the simple extension will be always finite extension. What does that mean? That means you can generate this is a finite dimensional vector space. What if? So how to write down? So let again that alpha belongs to some k over f. So k is the extension of f, is or rather be an algebraic element over f if and only if or I don't need late then. Okay, so just say that algebraic element if and only what? If and only if this simple extension this over f is a finite extension. What does that mean? This is finite dimensional vector space over f. Okay, so what does that mean? That means so we obviously got a proof for this. The proof is not so difficult. So it's if and only. So if alpha is algebraic, then something happened, and then if this is then so let you first choose first one. Let alpha is alpha be an algebraic element over f. And so what does that mean? That means it has a monic polynomial, right? And so you write down that if alpha x be the monic polynomial of alpha over f. Okay, so what does that mean? That means that is if alpha is this, we just prove it. Okay, and not only that, and degree of f alpha, which is you write down by this the dimension of f alpha over f, and this is nothing but degree of m alpha f, okay, which is finite, right? So sum n, okay, so f alpha over f is a finite extension of f, okay. So one part is obvious. Now conversely, we will prove that if it is finite extension, then this alpha must be a algebraic element. So conversely, if alpha, if the dimension of f alpha over s is something, say n, finite means it has to be some integer, right? So dimension cannot be fractions for the standard algebra. Okay, so obviously you can do something in calculus, fractional dimension, other things, Hausdorff dimension in topology, but I am not discussing that. Okay, so this algebraic dimension, so if it is n, we consider conversely let is equal to n. So now consider the set. So let us consider the set 1 alpha square alpha over n. Okay, this is a subset of f alpha, right? Well, because f alpha is a field, so all the elements belong to f alpha. Now you see that this set has maybe has n plus 1 elements and which is bigger than the degree of the extension, okay, is linearly dependent, right? Because if you have vector space of dimension n, you cannot have more than n many linearly independent vectors. So S must be linearly dependent. Over f. Okay. So once you know if S is linearly dependent over f, then you can find out some constant over f, such that these elements of the set S satisfy a non-trivial, a trivial relation with non-trivial coefficient, right? So thus there exists some C0, C1, Cn element of f, not all 0. You cannot all 0, right? Otherwise it will violate the property of linear dependence, such that what happened, C0 into okay, so did I start with, yeah, C0 into 1, so C1 into alpha, C2 into alpha square, and so on, Cn into alpha power n, that has to be equal to 0, right? This is the meaning of linear dependentness. Okay, and therefore alpha satisfies the following polynomial. Okay, so what is the polynomial? So this is fx equal to c0 plus c1x c2x square cn x power n. So alpha is the root of this following polynomial, right? And this is element of fx, right? So thus alpha is algebraic. over if. Okay, so what does that mean? That means whenever you have an element which is algebraic over if, this is if and only if that the simple extension generated by that element over the field must be finite extension. Okay, this is if and only conditions both sides. Okay, so what is the corollary of these things? So if you want to say some things about uh, algebraic extension, okay, so I don't know, okay, did I define something called algebraic extension? So maybe we can define. So if not, let me define here. So an extension K over F is said to be algebraic over if every element of K is algebraic over F. Okay, so if every element is algebraic, then we can say that the extension is algebraic over F. Okay, so what can we say from that the last theorem? We can say that if if K over F is a finite extension, then K is algebraic always, right? Over F. Okay, so and how do you prove that? So you start with, so obviously you need, the proof is simple and not difficult. So you need to prove that so let say K, the dimension of this is something, say, infinite, right? So I'm just assuming it, and you choose an element and alpha belongs to K, be an arbitrary element. What I'm doing, I'm taking that every arbitrary element is algebraic, right? I need to prove that, right? So you choose an arbitrary element, and now consider the subfield f alpha of K. See, f alpha is sitting inside K, because f is subfield of K and alpha belongs to K, so f alpha is a subfield of K, right? So because f alpha, if is finite, as K is finite over F, so if alpha is subfield of field K, so if alpha is also subfield. So which is also a finite x, right? Because the subfield of the bigger field, or bigger field is finite dimensional, so smaller field has to be finite dimensional, is also a finite extension of F, right? So thus, so now what you feel? So you just prove that if alpha over F is finite, I mean finite extension. When I say finite, I mean finite extension. An extension, this is finite. Okay, so alpha is algebraic. This is the previous theorem, we prove it. Okay, algebraic over F. So this is, what does that mean? Then every arbitrary element is algebraic over F. So thus K is an algebraic an algebraic extension. extension of if. Okay. Yes, so I think this is now fine, and you can easily check that. Okay, so yeah, so one more thing maybe I should tell here. So you say that the finite means algebraic. Okay, so what about like if I want to say that not exactly the dimension, for example, if I say that you choose an element to satisfy a n degree polynomial, okay, or if, then what will be the dimension of the simple extension f alpha over f, and that cannot be maximum n. It cannot be more than n, right? Because that polynomial may be irreducible, may not be irreducible, right? If it is irreducible, then dimension will be n. Otherwise, it will be something less than n, right? So if so that depends on the minimal polynomial. Okay. So what about the case when you have more than one extension? Okay. So do you have such a kind of relation among the dimension of tower of subfield? Okay. So let me start with this proposition or theorem. Um, so suppose you have, for example, you have a field K and then you have another field extension A, sorry, F and then K and then L. So let us do for 3 only, then we can do it for more also. So if you have this kind of uh, tower of fields, okay. So I let us assume this is finite. Otherwise, if infinite, the proof is almost trivial, okay, because the infinity will force, okay. So you can L over F is also vector space, and then L over K is vector space, and Ky is also vector space, right? So now do we have any relation among the dimension of these two things, these three fields? Okay, and the answer is then you can say that the dimension of L over F as a vector space. So I'm assuming that this is a finite. So okay, so they are finite extension. If not finite, if any of those things infinite, then you can easily, and I'll tell you, it's obvious, right? Okay, so okay, so I'm assuming that. So then what happened? Then this dimension is nothing but the product of the individual dimension. So if you first go from F to K, so dimension of K over F, and then K to L, so dimension of L over K. Okay, so this require a proof. This is a very important theorem, and they require a proper proof. So now how do we prove it? So let us assume that okay, so maybe I can assume that this dimension is something say m, and this is say n, and I will prove that this has to be m into n. Then I am done, because yeah, so this product will be this. Okay, now how do you prove it? So I assume that L over K is Ky is n, L over K is m, then it is mn or nm or whatever. Okay. So as dimension of L over K is m, we will have a basis of mn elements. Okay, we have a basis, say b1 of m many elements, and so let me write down the elements is alpha 1, alpha 2, alpha m, basis of L over K. Okay. Similarly, as K over F has dimension n, so we have we have a basis, say b2, and say something, say beta 1, beta 2, and say beta n, and this is basis of k over f. Okay, so we have two bases, and now I am claiming that the product alpha and beta j is a basis over. So this is my claim. So the product alpha I beta j, and this I equal to 1 to m, right? Alpha is from 1 to m, I guess, yes. And j equal to say 1 to n is a basis of L over the field, the base field F. So this is my claim. So if I prove this, then I am done. Then it will be actually product of m into n, right? Okay, now recall that to prove something is a basis, what you need to prove? You need to prove two things. It is a linearly independent set, and this is also a spanning set. Now how do you prove this is a linearly independent set? So to prove something is a linear independent set, what you need to prove? So to prove that if you have any trivial combination with linear combination of alpha I beta j, then the the coefficient must be 0 for all the coefficients, all ij, right? So you start with a combination, say maybe Cij alpha I beta j, and this is running over I and j. I is from 1 to n, j is from 1 to n, 0 for some Cij belongs to f. Okay, so I am proving that L over f has the basis alpha I beta j. So I choose a linear combination which is 0, and I need to show that the coefficients are 0, right? Now so this is so I need to prove that all theCij's are 0, right? Okay, so now now consider the following identities or equation, whatever. So I'm writing what? I'm writing this Cij alpha I. I'm writing this is another element. So see, alpha ij's are element of what? So you should understand that first. Okay, this alpha 1, alpha 2, alpha 3, alpha m, they are basis of L over k. So this alpha is an element of L. Similarly, beta 1, beta 2, element, this is basis over k over f. So beta i's are element of k, right? So what I can do, okay, so I can do two things. So one is, okay, so alpha, okay, okay, so let me define my constant aij by this ai. Okay, yeah, so ai, so following, so I'm defining this ai is summation Cij beta j, okay, j over 1 to n. Okay, if we take this sum, so this will be something involving I, right? Because in the right hand side the sum is over j. So these ai's are what? These ai's are element of k, right? Because you just see that this beta 1, beta 2, beta n are element of k, and if you take linear combination of the field of k, so that will be element of k. So all those ai's are element of k. So if you write down ai equal to summation Cij bi, and then you have this equation, so equation star, so then then equation star becomes, so you can write down the equation star in terms of AIs. How you can write down? So this becomes so this Cij Bj equal to AI, so this is AI alpha I, right? This summation over I AI alpha I, that equal to 0. Okay, that is 0, and with AI element of k, right? Now okay, now note that because this is a basis, right? So this alpha 1, alpha 2, alpha a, alpha m linearly independent are linearly independent over k, right? Because this is a basis of L over k, we have what we have ai equal to 0 for all I equal to 1 to m, right? Because what if alpha I are linear independent, if you take any such combination it is 0, then alpha has to be 0, ai has to be 0, the coefficients, right? So ai's are all 0. So thus now this is equation maybe double star. Okay, so thus this double star becomes, what you can say? You can say that all the ai's are 0, right? So what does that mean? That means summation Cij beta j and j equal to say 1 to n. This is 0, right? 0 for all I. Okay. So what does that mean? Again, you see that beta 1, beta 2, beta n, these are basis. This forms a basis, right? Forms a basis of k over f, and UCIJs are element of f, right? Again the linear independence of this beta 1, beta 2 and beta n over if this is independent over f, right? We have this for all I, remember, for all I equal to 1 to m. What do we have? We have Cij is 0, and that is true for every I, every a, for all I equal to 1 to m and j equal to 1 to n. Okay, so this is my goal actually. Thus this set, what was the name of the set I gave? I did not give any name. Maybe let me write down S, the set S alpha I beta j, the same ij is linearly independent over f. Okay, so this is a set of the vectors of L which is linearly independent over the field F, right? So one part you already get the linear independence property. What is the next part? Next part is that spanning set that you need to prove, and that is also not difficult. Okay, now to prove that is a generating set, a spanning set, whatever set for L over F. What do you have? So you just consider, okay, F, so let you choose some element. X belongs to L, X is element of L. Then there exists, you can have say some A1, A2, A M belongs to K, such that, because you know that alpha 1, alpha 2, alpha is the basis, so you can have X can be written as A1 alpha 1 plus A2 alpha 2 and dot 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 AM alpha M, right? And this AI is an element of K, right? Okay, so AI is an element of K, I can write down that thing. So again as K over F has a basis. What was the basis I wrote? Somewhere here. B2, yeah, so this is the basis B2. This is B2. So we can write this AIs as linear combination of the basis element of this beta 2 as B2s. So you can write down A equal to some basis element, so maybe so I, right? So the first one is I, so something say bi 1 and basis, right? So beta 1, similarly bi 2, beta 2, and so on, bi n, beta n. Okay, this I stands for the ith number of this Aij, and this 1, 2, 3, 4 are correspond to this basis element beta 1, beta 2, beta n. So in general, you can write down AI equal to B summation Bij beta j equal to 1 to n. So this is AI equal to this. This is in general, you can write it down. Okay. Now Aij equal to, you can write down this, and obviously you have this equation X. So thus you can write down X as in terms of summation, double summation over I and j, and so you substitute this value, then what happens? You have beta Ij alpha I beta j, right? Because you already have alpha I here. Summation Aij, summation AI alpha I. Now AI is also summation beta Ij. Where is that? Yeah, beta Ij, Bij beta j. So if you replace that thing, then you have X equal to this is a linear combination of alpha I beta j over the field F. Okay, thus this is set S alpha I beta j I1 less than equal to n, j less than equal to n1 is a spanning set. For L over F. Okay, so yeah, so I mean, don't write so. Yeah, so spanning set, what does that mean? That means is a basis, right? Okay, so hence we have, what do we have? We have this dimension of the L over F is equal to that K over F and then L over K. Okay, hence proof. Okay, so now if any one of those things infinite, then what happens? So for example, if this is infinite, say, I mean if this k over f infinite, then what happens? That means that there are infinitely many elements of k which are linearly independent over f, right? But those infinite element of k which are linearly independent over f are also element of L. So they are also linearly over f, right? So that means this implies this is also infinite, right? Clear? And now obviously if you assume this also same thing, okay, so whatever. Now conversely, if you have this, suppose um, L over f is infinite, then at least one of them has to be infinite, because both cannot be finite. If both are finite, then the product is finite, right? So this become finite. Okay, so um, both find infinite, then this has to be then at least one of this and this is infinite. Okay, so that is the proof. So this identity is true for infinite also, so it's not only true for finite thing. Okay, so obviously you can easily say that whenever you have a subfield of any field extension and you have finite extension, obviously, and then these dimension that they divide this dimension, or this dimension divides this dimension. This is obvious, right? Because this product is this, right? So you can just say corollary that suppose you have like L over k over f, and then such that L over f is finite, then this any extension, this dimension, it always divides the dimension of L over f, and that is immediate, right? Okay, so I mean I am not writing because you only prove it that this is product of this into L over k, so it's obvious, right? Okay, so maybe I can give some example here. So so suppose I have say q, and then say q root 2. Okay. This is a finite extension and degree 2 extension, and you see that you can over q root 2 root 3 is also irreducible, so you can talk about q root 2 of root 3. Okay, actually it is actually q of root 2 root 3. I mean this is almost obvious, but if you need a proof, then I can give a proof. Okay, so okay, so yeah, so this is also degree 2 extension. Now you see that you can have so this is degree 4 extension, this is degree 4 extension 2 into 2, right? Now one more thing, so you can find out see this is finite extension, no? So this is also algebraic, so this is algebraic over q, right? And so these finite extensions which is of q, these are called algebraic number fields. Actually they are called algebraic number fields are finite extension of of rational numbers. Okay, so the algebraic extension, they find extension of rational number. Now obviously you can ask me how do you know that this is irreducible. So that this is another proof. We can prove that root 3 is irreducible over q root 2. Okay, and minimal polynomial. So like minimal polynomial. So m root 2 q. This is x square minus 2. But m root 3, and then you just attach q root 2 of x. You see that this is x square minus 3. So what does that mean? That means root 3 is an algebraic element of over q root 2 of degree 2, and this is a minimal polynomial. You can easily find out. Okay, and hence you can easily check that the minimal polynomial of okay, so I'm claiming that this is also generated by a single element. And now what is that element? Alpha, that will generate this thing. And I'm claiming that this root 2 plus root 3, this is the element. You check that this minimal polynomial, this degree is actually 4, and that is this minimal polynomial of this over f q. Okay, now how do you get the minimal polynomial of this kind of polynomial? Obviously you can think that is a product of these two things, or you can directly check what is that. And to check directly, so this is the root of that polynomial, right? So what does that mean? That means x minus root 2 whole square has to be equal to 3, right? So if it is root of x plus root 3 is a root of something, so it has to be 3, and that will gives you that the polynomial will be of the form x square minus 2 times root 2 of x plus 2, that equal to 3, right? And that will gives you that x square, and then it will come this side, so minus 1 equal to 2 root 2x, right? And now you have to make it over q, so you need to take square also, so you'll have x square minus 1, that whole square equal to 2 square 4 into 2 8x, right? And this will gives you x to the power 4. So you understood that if x equal to root 2 plus root 3, then that satisfies this equation, and then go on. So this will gives you this, and then this will gives you this, and then you'll have minus 1, and then this, so 8. So this is this minus 2x square plus 1 minus 8x equal to 0. So what does that mean? That means x to the power 4 x to the power 4 minus 2x square minus 8x. Right? Let me check it. X to the 4 minus 2x minus x plus 1. So x to the 4 minus 2x square minus 8x plus 1 equal to 0, right? So what does that mean? That means if you choose fx equal to the polynomial x power 4 minus 2x minus 8x plus 1, so this is a polynomial over q which is irreducible of degree 4. Now you see that this, if you take the product of these two polynomials, this is no longer irreducible, right? So this x square minus 2 into x square minus 3 is not irreducible over q, right? And hence you cannot directly say that, but here you can say that. Now can you say that this is irreducible? Now prove it. It's irreducible over Q. Okay. So, and the homework. You check that this is an irreducible polynomial over Q, and done. So that gives you the fact that that you have a element of degree 4, and hence this is a simple extension, because the degree is 4 already. You know that this is tower of fields, right? It's a product of 2 into 2 equal to 4. So you need to find out an element whose degree is also 4, and that will generate the extension, and hence this is a simple extension. Okay, so this is homework. I will ask you for a proof next day, and I hope you can easily prove it. Okay, so I will stop here for my today's lecture. In my next lecture, I will talk about a little bit more about how to find out, for example, algebraic clues and other things. Okay, so I'll stop here now.